Hello. Now our next lecture is actually the same topic, that size dependency of different nanoparticles, but here only the properties is going to be changed. That is, in our last lecture we have discussed about that electrodeposition techniques or maybe some kind of electrochemical techniques. Now here in this particular case just we are concentrating onto the mechanical properties of that particular nanoparticles. So here just we are going to see that if we are changing the size from that micro to nano, that how the mechanical properties is going to be changed for these particular nano composites. So size plays a vital role in mechanical properties of nanostructured coatings. So this is the general idea actually. So here these lines actually, or maybe these statements we are going to prove in our next subsequent slides. So when we are reducing our size from micro or macro to nano, the automatically the mechanical properties in terms of tensile strength, elongation at break, or maybe the tear properties, or maybe some other mechanical properties of that particular nanocomposites is going to be changed. Plastic deformation of a nanostructure coating strictly depends on its grain size. That means grain size is nothing but the crystallite size of that particular nanoparticles. With decrease in grain size beyond certain limit, Hall patch equation does not apply, and contrary to expectations, this indicates that particular materials will become softer. So this is also one kind of considerations for these particular techniques. Reduction of granule size has remarkable effect on improvement of resistance against erosions in nanostructure and composite materials. So that is also one kind of added advantage, that when we are using some kind of smaller nanoparticles than the previous one, or maybe than the bulk one, so we are getting the best erosion properties in terms of mechanical properties. Erosion behavior under low and average loading conditions in nanomaterials shows that because of higher stiffness, erosion resistance to these materials is more than that of materials with the large size. So the erosion properties of that particular material is getting enhanced, so that the material erosion properties is going to be decreased when we are decreasing the particle size from micro or macro to nano. Creep in nanostructured materials is more than microcrystal materials, since grain boundary slips is regarded as one of the mechanism of creep. So here that when we are talking about the microcrystals, the creep is more, but when we are talking about some kind of materials which is having the nanoparticles, that particles into the nanometer range, the creep of that particular material is going to be reduced. Next, effect of size on mechanical properties. Mechanical properties of small scale structures are different from those of the conventional or bulk structures. We have discussed these lines several times. Effective elastic properties of these small scale structural elements strongly depend on their size. Small scale structures are very sensitive to the microstructural features of the material, such as grain size, the finite number of grains, the boundary layer thickness, texture, and the dislocation structure. That means its total properties is totally depend upon the crystallite size, that how the material is behaving, what are the average diameter of that particular material, how the grain boundary is forming, and then what is the dislocation of this kind of grain boundary. So all actually depends upon the crystallite size of that particular material. Research studies have shown that when particles size reaches to the dimension of nanometer, remarkable improvement can be observed in strength of composites. In nanoscale bars and plates, effective elastic properties of structural elements strongly depend on their size. It was found that a nano whisker can have a mechanical strength approaching to the theoretical strength values. The increase of mechanical strength becomes appreciable only when the diameter of a whisker is less than 10 microns. So from this particular statement we can understand that when the whisker size we are reducing from the micron level to the nano level, so automatically the mechanical properties is enhancing for that particular composites. So here is the empirical Hall patch model, or maybe that well known Hall patch model, generally by which we are calculating the total grain boundaries of that particular materials. The Hall patch model treats the grain boundaries as boundaries to dislocation motions, and thus dislocation pile up against the boundary. Upon reaching a critical stress, the dislocations will cross over to the next grain and induce yielding. The Hall patch model is given as below, because when you are talking about the grain size is well distributed inside the composites. If there is if there is some kind of straining or maybe some kind of difficult occurs to a particular grain, then after certain time it will induce to the next grain boundaries, and that next grain boundaries will be affected by these grain boundaries. So this is the empirical Hall patch model, which is given below is capital H is equal to H0 plus Kh by root over d, where H is the yield stress, H0 is the materials constant which actually depends upon that particular material properties, Kh is the strengthening coefficient, and D is the average grain size of that particular materials. So here the comparison of stress and strain for nanocrystalline and microcrystalline copper. So here this is the two stress which is showing into the y axis, and the unit of that is megapascal, and this is the two strain which is into the percentage manner in the x axis. So when we are talking about some kind of nanocrystalline copper, so when it is into the microcrystalline particle size, it is showing the stress up to maybe the 200 megapascal, but when the nanocrystalline copper means particle size into the nano scale, the automatic particle size is going around 400 the two stress is going around 400 megapascal at that particular case. That means that when we are decreasing the particle size from micro to nano, the true stress of that particular material is changing or almost the double. Here is also an examples. The mechanical strength of sodium chloride whiskers increases significantly and approaches the theoretical strength as particle size decrease. Nanomaterials such as whiskers possess high perfections and no dislocations have been found in nanostructured materials. Therefore, the Hall patch model should be invalidated in the nanometer regime. So that is also one aspect of this particular technology. Nanostructured materials may have different elastoplasticity from that of large grain bulk materials. For example, near perfect elastoplasticity was observed in pure nanocrystalline copper prepared by means of powder metallurgy. So in that particular case, for a single material, when we are changing the diameter size or of that particular particulate, we can see that the strength of that particular material is drastically changing. It is directly coming from the 100 to almost 0, then when we are actually increasing the diameter into the micrometer level. So from small particle to bigger particle, when we are changing our composite particulate size, the strength is totally decreasing at that particular point. Then we are going to discuss about the size effect on hardness and strength of nanostructures. So following mechanical properties were significantly affected by the grain size. One is called the hardness, another one is called the yield strength and tensional strength, and third one is called the malleability. So these all three are the material's inherent property which is going to be changed when we are using the particulate size from micro to nano. Here this is an examples that if we are putting the grain size into the x axis and we are putting the hardness into the y axis, we can see that hardness simple, it is starting from the low value, then sudden it is going to the higher value, then it is almost the same when we are increasing the grain size. So that means when the particles into the amorphous regions, its hardness is little bit low, but when the particle size is going into the nanoscale size or maybe the nanometer range, then certainly the hardness is increasing tremendously, but when the particle again we are going into the micro sizes, so automatically the hardness is going drastically decreased. So what is the hardness? in nano coatings, an increase in grain size is accompanied with considerable decrease of hardness in range of lower than 20 nanometer. These observed results of hardness are not correspondent with Hall patch behavior, as grain size decreases, hardness increases. So, we have already told into the nanometer range the Hall patch relations is actually not working properly. It is interesting to know that work coefficient of hardness decrease to around 0 when the grain size reduces up to 10 nanometer. So, here also the same thing. So, when we are having the in the amorphous regions, the hardness is moderate, but when we are going to the nanocrystalline regions, that hardness is tremendously increasing. So, that is due to the intergranular processes, small scale sliding in the grain boundaries, and then due to the enhanced hardness is occurring due to the nanostructure in that particular zone. Then intergranular process is starting, that means dislocation, nucleation and motion is taking place. That is why when the size is going from nano to the micro, then automatically the hardness is getting to be reduced. Then in terms of yield strength and tensile strength, tensional strength increase with grain size decreases, well as considerable increase in hardness. So, when we are seeing the grain size, then in terms of tensile strength it is changing very rapidly, it is increasing in a very rapid manner, and also the vice versa is taking place when we are talking about the failure strain. So, when the grain size is increasing, then the failure strain is also decreasing in that manner. So, yield strength and tensile strength increase with grain size decreases, well as considerable increase in hardness. Plastic deformation behavior of nanocrystalline materials is strongly dependent on grain size. For FCC metals, dislocation mechanisms is not used for nanocrystalline materials having grain size lower than 10 nanometer. Then we can see that malleability property, which is also one kind of mechanical properties of that particular metals, or maybe that some metals. Then malleability of materials is directly proportional to the strength. It means if strength increases, malleability increases, that is the standard thinking in our mind. So, for typical materials, reduction in grain size will lead to decrease in materials malleability. Figure here shows that as the aluminum particle size increases from nanometer to micrometer, the strength is totally decreasing. When the strength is totally decreasing, that means the malleability is also totally decreasing, because strength is directly proportional to the malleability. So, if the strength will increase, the malleability will also increase, and if the strength will decrease, the malleability will also decrease. So, when the strength is decreasing, simultaneously the malleability will be also decreasing. Then how to enhance the strength into the nanostructure systems. The emerging areas of micro and nanotechnologies exhibit important strength differences. The result from continuous modification of the material microstructural characteristics with changing size, whereby the smaller is the size, the stronger is the response. So, increase in strength has been observed by decreasing particle size of particle reinforced composites while keeping the volume fraction constant, diameter of micro wears under torsions, thickness of thin films under bending or uniaxial tensions, grain size of nanocrystalline materials, and the void size in nanoporous media. So, when we are increasing the strength or maybe has been observed by decreasing, so this can be occurred inside the material itself, or maybe these properties we can see from that material's point of view. So, here is the figure which is A is showing the stress strain diagrams for various sizes. Then when we are changing the size, how the stress is varying in terms of strain, and not only that, the right hand side figure it is showing the change in yield strength or the rate of strain hardening as the size decreases. So, how this mechanical properties is changing depending upon the crystallite size of that particular nanocomposites or maybe the coating. Then mechanism of the strength enhancement, two possible mechanisms actually are available. Depending upon that, there are two schools, those who are thinking these two different mechanisms. So, two possible mechanisms have been proposed to explain the enhanced strength of whiskers. Firstly, strength enhancement is due to the high internal perfections of the nanoware or whiskers. So, this is one vital parameter, is high internal perfections. The smaller the cross section of a whisker or nanowires, the less is the probability of finding it in any imperfections such as dislocations, microtwins, impurity precipitation, etc. So, automatically if the crystallite size will be smaller, then the chance of impurities or maybe that imperfection will be getting low. Secondly, the strength enhancement is due to the perfection of the side faces. This is also the another thinking, that perfection of the side faces of whiskers or nanowires. In general, smaller structures have less surface defects. So, if we see at the end of the day, maybe these two theories are almost same, but still there are two different thinkings by the scientist itself. Then size effect in mechanical properties of 2D nanofilms. So, when you are talking about the nanofilms, it is 2D in structure. So, the how the mechanical properties is affecting on based on the size of that particular particles. A continuum model based on surface elasticity is proposed to analyze the size dependent mechanical response of ultra thin elastic films of nanoscale thickness. From the continuum point of view, a surface is regarded as a negligibly thin object adhering to the underlying material without slipping, and the materials constant for both are different. The size dependency is due to the dependence of surface stress on strain. The presence of surface limb constants and residual surface tensions under unconstant conditions increases and decreases the film stiffness respectively. So, here is the example, the effect of the materials microstructural interface increases as surface to volume ratio increases. So, this is the main message of this particular lecture. So, here the film thickness is h, small h, radius of circular film is capital R through the thickness, ratio is x3 by h, dimensionless transverse shear stress is sigma, and the intrinsic length is eta. So, though the thickness distribution of dimensionless transverse shear stress at r small r is equal to capital R by 2. Then size dependency on tensile and fatigue strength on ultra thin films. Then fatigue strength as a function of film thickness was measured under the constant constant total strain range control at a frequency of 10 Hz. The experimental results exhibit that both yield strength and fatigue lifetime are dependent on film thickness. It can be noticed here that the yield strength of ultra thin copper films further increases with decreasing film thickness down to several tens of nanometers. So, here we can see that when we are changing the crystallite size, how the yield strength is changing, where still the film thickness is also increasing. So, film thickness is increasing from 40 to 140 nanometer, yield strength is changing it from 400 to 1600 megapascal. So, at 50 nanometer, whatever the yield strength is occurring, when you are applying the 60 nanometer crystallite size, though the film thickness is also increasing, but it is showing the maximum yield strength at that particular point. Fatigue damage behavior in 100 nanometer thick copper films having nanometer size grains is different from that in micrometer thick copper films having large grains. Fatigue of thin metal films is a key issue for the long term service of micro devices. Investigations of fatigue of thin metal foils show a tremendously tendency of improved fatigue strength with decreasing foil thickness. Fatigue resistance of the ultra thin copper films is higher than those of the micrometer thick films, but somewhat less than that of sub micrometer thick films. It is suggested that the activated grain boundary related deformation mechanisms is responsible for the potential decrease in the fatigue resistance in the nanometer thick films compared with the sub micrometer thick films. These all are the obtained result from this particular slide. So, here figure A, the mechanical energy loss versus the number of cycles of the 60 nanometer thick copper films, it is showing like this, and the right hand side figure which is giving the number of cycles of fatigue damage as a function of film thickness. Then the size dependency in nanocomposite layers. So, in this particular case we are going to see that how the particle size is affecting the surface roughness of that particular materials or maybe of that particular nanocomposites or maybe that coatings. So, effect of particle size on roughness of silicon nitride, then silica and oblique nickel composites. So, here it is a hybrid kind of composites in where the interpolated equation shows that there is a quadratic relations among the roughness of obtained layer and ASNP, average size of nanometric particulate. This shows that the interaction among nanoparticulates with low ASNP approximately less than 90 nanometer will increase the roughness of obtained layer. Minimum roughness has been obtained for nanocomposite layer with ASNP equal to 93 nanometer. So, here this is the roughness generally we are giving in nanometer range. Here is the average size of nanometric particles. From this particular case you can see that when we are increasing the particle size up to certain time the roughness is reducing, but after that the agglomerations of particle is taking place when you are increasing the more particles, that is why certainly the roughness is again increasing. So, effect of different ASNP on the surface roughness value which is known as the RA of electroplated nanocomposites silicon nitride nickel coatings. Then effect of particle size on roughness of tungsten carbide nanoparticles. Here the tungsten carbide nanoparticles probably act as new sites for grain growth and hence decreases the final size of the grains. RA values of the nanocomposites layers were observed approx between 1.6 to 4.9 micrometer. RA is nothing but the surface roughness of that particular material. So, increase of roughness is due to the agglomeration of tungsten carbide nanoparticles on the surface of the treated sample. So, as I told already, sometimes the agglomeration is taking place. Concentration of tungsten carbide nanoparticles in the electrolyte has an optimum level for achieving the minimum roughness on the surface of the nanocomposite layer at higher current densities. In fact, the increase of nanoparticle concentration in the electrolyte and the increase of the current densities have similar effects on surface roughness. Higher current densities will lead to big sparks with more damaging effects, and their effects will show themselves on low concentration of nanoparticles in the electrolyte. So, here we are showing that how the material is changing in terms of nanoparticles concentration of tungsten carbide, and here is the surface roughness values. So, relations among surface roughness of coating and tungsten carbide nanoparticle concentration in a electrolyte in different current densities. So, first one is 1.2 ampere per centimeter square, the next is that 0.8 ampere per centimeter square, and the next one is 0.2 ampere per centimeter square. So, different current densities, how the tungsten carbide nanoparticles concentration is totally changing and how the roughness is totally changing. Then effect of ASNP on distribution of nanometric particulates. So, distribution of silicon nitride and nickel electroplated nanocomposite layer have been studied. We have shown so many results in our last slide also. So, it can be easily concluded that the Gaussian shape of distribution curves are narrower for lower amounts of ASNP, but if we increase the percentage of that ASNP, so we can see the Gaussian curve will be more broader. So, also it can be seen that the distribution curves of obtained layer for higher amount of ASNP are wider, which means that although the nanometric powders with narrow distributions of particulates around the specific ASNP have been used, but the distribution of nanometric particulates in obtained nanocomposite layer is not as same as the distribution of such particulates having large ASNP. So, if average diameter of that particle will be increased, then it will cover the large area and also some kind of small particle will fill up those gap, but if the average diameter size will be less, then there will be very uncovered area. So, that is why the Gaussian curve is not the wider one. So, therefore, it is better to use the nanometric particulates for fabrication of nanocomposite layer with lower amounts of ASNP having narrower Gaussian shapes. So, distribution curves of electroplated nanocomposite, silicon nitride and nickel coatings with ASNP equal to 9 nanometers is A, then 72 nanometers, then 168 nanometers and the 499 nanometers where you are getting a border spectrum of Gaussian curve. Then effect of particle size on wear. So, example is that it has been observed that by adding quantum dots nanoparticulates, the electrical conductivity of layers is completely controllable without adverse effect on wear resistance. Effect of addition quantum dots on wear rate of a hard nanocomposite shows an optimum level, and increasing the silicon dioxide quantum dot ratio after this level will decrease wear rate significantly. Similar effects were observed with ultra hard ceramic nanocomposite layers of tungsten carbide on matrix of titanium carbide. So, here we are showing that effect of silicon dioxide quantum dot ratio on wear rate of silica epoxy nanocomposites layer. So, when we are changing the ratio of silicon dioxide and quantum dots, we can see that wear rate certainly it is increasing, but simultaneously the ratio when it is increasing then automatically it is going down. So, that means it depends upon the particle size of silicon dioxide and quantum dots which is affecting the wear properties in this particular system. Then next is that effect of particle size on wear of alumina, yttrium oxide and carbon nanotube nanocomposites layer. So, electrodeposition of tertiary alumina, yttria, carbon nanotube nanocomposite layer using pulsed current. Wear properties of coating significantly changes with change in size of the nanoparticles. So, from this particular figure we can understand that there is a relation in between the wear rate and the average size of nanoparticles. So, automatically it is going in a standard manner. So, relation between average size of nanoparticles and wear rates for electrodeposited tertiary nanocomposites layer is showing and increasing in a standard manner. Then we are coming to our last slides which will give a glimpse of our this lecture which we are now discussing actually. So, grain size of nanoparticles and coating thickness play vital role in tailoring mechanical properties of nanostructured coatings. Plastic deformation of nanostructure coating strictly depends on its grain size. With decreasing grain size beyond certain limit, Hall patch effect does not valid. Properties like strength, hardness, fatigue strength, creep and wear are also highly dependent on the grain size. Roughness, resistance against oxidization, thermal conductivity were mostly found to be dependent on coating thickness. So, these all are the points we have extensively discussed in this particular lecture. Thank you.